start the recording. Okay, so today we'll talk about, we'll extend our study on Bohr's theory. Okay, so last day we talk about some spectra and all. So first of all, let us first write the energy equation again, which is E n is equals to minus is there m, what was that energy equation? mz square কি আসলে e to the power
e to the power 4
okay divided by
8 epsilon naught square
okay
h square
into 1 by n square, isn't it? Okay, so we had this energy value, the total energy of an electron moving in a hydrogen atom. Okay, not hydrogen atom, any atom. If we put Z equal to 1, then it's become hydrogen atom. Now there is a thing called term value. Okay, there is a thing called term value. Your importance ami gom pam when we study spectra and all in molecular physics, but right now to me just term value boli bostota monot thwa. Term value means simple, you just need to divide your energy by hc. You can say minus hc. Okay, so the term value I'm just representing by Tn. So Tn is equals to energy divided by minus hc. Minus is just put to cancel out the minus sign already present in the energy value, because term value is always positive. So why we need term value? Okay, first of all, you try and find out the dimension of term value. Let me see if someone has just joined. Let me admit him. Okay. Okay, so term value, first of all, you just find out the dimension of term value. You have to divide energy by Planck constant and velocity of light. ঠিক আছে, velocity of, again someone has joined. Okay, okay, so we have to divide energy by hc. H is the Planck's constant, c is the velocity of light. So তুমি check করি সাবা যে তুমি কি unit পোৱা. Generally we represent term value in centimeter inverse. Okay, now this centimeter inverse has a very huge significance in our study of atomic spectra. Using centimeter inverse, you can represent wavelength, sorry, inverse of the wavelength. Wavelength মানে centimeter আহি যাব unit. যদি 1 by lambda করো, centimeter inverse আহিব. With centimeter inverse, you can represent the term energy as well. Energy means term value as well. Term value is also type of energy বুজোৱা নিচিনাকে বুজায়. Okay, so centimeter inverse তুমি বহুত দেখিবা এটা খুব ইউজ কৰা হয় তোমাৰ atomic spectra হওক লাগিলে molecular spectra হওক. When they need to represent energy scale তুমি চাবা they won't give you energy scale in electron volt or joule or those. They will just simply represent energy scale in centimeter inverse. Okay, now we will use this thing in the future. Okay, just for the moment, just remember term value is energy divided by hc, putting the minus sign just to cancel out this minus sign. Okay, and the unit will be centimeter inverse. This is known as term value. Okay, now again we get back to this equation, the main equation. Okay, in this equation, if I put suppose I can make out a constant from there. In this equation, m e to the power 4 divided by 8 epsilon naught square h square. Okay, this seems to be a constant. I'm not bringing z also here. Z can be a different atomic number. So this comes out to be a constant. And let us represent this constant as r infinity. Okay, why I'm putting this infinity term here, I'll explain you within a minute. Okay, so this known as Rydberg constant. You have heard about Rydberg constant. Okay, Rydberg constant in your HS, you have heard about this Rydberg constant. For infinite, I'm using the infinity sign here. So it has to represent something infinity. So I'm saying here Rydberg constant for infinite mass of nucleus. Now, why I'm using this word infinite mass of nucleus? In the last class, means the yesterday class in our general class, there I said that in our assumption, we have considered that the nucleus is stationary and the electron is revolving around the nucleus. Stationary means nucleus is too heavy and electron is moving. Okay, and we said that this can be false. It tomar bhulo hobo pare. Jodi hetu bhul hoy, that means if nucleus is also moving, then your mass will be changed and it will be replaced by reduced mass. আমি অলপ কথা পাতিছিলো কালি তাৰ বিষয়তে. Okay, so I am using this Rydberg constant infinity term here just to show that I am using this constant for infinite mass of nucleus. Means I'm just using the general concept of Bohr, where Bohr hasn't talked about anything where nucleus is moving. So ধরে লইছিলে বোরে যে nucleus is rest. At rest means it's too heavy to move. Okay, that was the consideration of the Bohr, and that's why I'm putting R is infinity equal to this. কারণ যদি মই m or value change কৰি দিও, reduce mass কৰি দিও, then এই R infinity নহব, এটো বেলেগ কিবা এটা constant হ'ব. Okay, we'll also do that. Okay, so for the moment, just going by the Bohr's postulate, and we are considering that nucleus is not moving. Nucleus is very heavy, it's not moving, only electron is moving, and I'm just putting this whole constant term in a by replacing the whole constant term by a single constant, which is known as Rydberg constant. I'm putting the infinity sign here to show that this constant is representing a system where the nucleus is very heavy and it's not moving. Okay, infinitely heavy mass. Okay, this is R infinity. So now if I rewrite my energy expression, it will become like En is equals to minus R infinity Z square divided by N square. Okay, this is my final expression for energy value equation. Okay, so if my electron, suppose say these are the energy levels. Okay, now I come to know that energy levels are discrete because n value can go from 1 2 3 4 ne goi thakibo. Okay, so 1 2 3 hoi thakibo n value, that means energy values are different. Je tumi n equal to 1 put koras for hydrogen atom, suppose z is equal to 1, R infinity already has a constant value. So if you put n equal to 1, you'll get minus 13.6. If you put n equal to 2, you'll get minus 3.6, like that. That means we have discrete energy levels. Okay, so say this is n is equal to 1, n is equal to 2, n equal to 3. Now suppose your electron is at rest in first orbit, suppose it is here, n equal to 1. Now because of some source of energy, suppose source of energy ahile bahir pora input hole, then this electron will jump, and this electron will go to it can go to this level, or it can go to directly to the n equal to 3. Okay, this is the transition. So if I say this is my initial stage, this is my initial stage, then this is my final stage. Okay, I'm getting a call, so just give me a okay, just cut. Okay, no issue. Okay, so the electron will jump from n equal to 1 to n equal to 2 or n equal to 3. Okay, so this n equal to 1 becomes the initial level, and 2 or 3 or even 4 5 whatever it is, it will become final level. So if you want to know how much energy is absorbed by the electron by moving from n equal to 1 to say n equal to 2, then what you have to do, first you have to calculate the values, or you can do like this, say En1 will be simply minus R infinity Z square, say N1 square. I'm not saying is n equal to 1, I'm just saying N1. Okay, N1 is the initial value, or I can put Ni, let us say Ni, and similarly the final where the electron has reached after absorbing the energy, say it's final NF, and we get R infinity Z square divided by NF square. Okay. Now, this electron is moving from n equal to 1 to 2, 3, whatever, by absorbing some kind of radiation from outside, some kind of energy. Okay. So it's absorbing some kind of energy from outside. How much energy will it absorb? It will absorb the energy which is required to move from 1 to 2. Suppose from 1 to 2, to move from 1 to 2, it requires 10 electron volt energy. And corresponding to our frequency yellow para, I'll give you a formula. 1240 divided by lambda in nanometer is equals to energy in electron volt. Okay, you can use this formula to always find out the corresponding energies, corresponding wavelength. Suppose energy is 3 electron volt, then corresponding wavelength ki mano. Simply take lambda this side, energy this side, divide 1240 by 3. So for 3 electron volt, you'll get around 410 nanometer wavelength. Okay, it's a relation. You just remember this. Your lambda is in nanometer and this electron volt is energy in electron volt. Okay, so if you have 3 electron volt, that means you'll have lambda in nanometer. You'll have simply 1240 by 3. You'll get around 410, 400, I think 13 something, 0.33 nanometer. Similarly, 4 hole aru kom hobo. Okay, so that means when some kind of radiation is coming, say for electron to jump from n equal to 1 to n equal to 2, it requires around 300 nanometer wavelength. So if 300 nanometer wavelengths come here, it will directly absorb all the wavelength of 300 nanometer, the energy carries by 300 nanometer, and jump from n equal to 2. Suppose from n equal to 1 to n equal to 3, it requires suppose 500 nanometer wavelength. Okay, or maybe it requires 200 nanometer wavelength. Then it will absorb the whole and go to there. So what I'm saying, how much energy absorbed in terms of frequency while jumping from the initial state to final state can be calculated like this. Suppose from E and I, and I'm writing here E and F minus, means final stage energy minus initial stage, is simply equal to h nu. Okay, how much energy absorb koile is simply is equals to h nu, or you can write hc by lambda. So or I can write h nu is equals to, I can put all those values of nf and already I got here. After doing all that, you'll get something like this. Your nu, let us do it. H nu is equals to ENF ki asile minus R infinity Z square by NF square minus plus R infinity Z square by Ni square. Or I can take R infinity and Z square outside. What we left inside? We left 1 by Ni square minus 1 by NF square. Okay, and this side we have H nu. Okay, or I can write hc by lambda, and we have the same expression here. Or I can put 1 by lambda this side, and this R infinity Z square divided by, we have now hc, and we have 1 by Ni square minus 1 by NF square. Okay, so 1 by lambda, the unit will be in meter inverse, or in if you do CGS, you will have say centimeter inverse. Okay. Now, for the electron, when it moves from initial stage Ni to NF, it will absorb this much of energy, or in terms of wavelength, para. Okay. Okay. Sometime you'll get minus sign here. তুমি কেতিয়াবা নেগেটিভ পাব পাৰা কেতিয়াবা পজিটিভ পাব পাৰা sometimes you will see ইয়াত ni দেখিবা ইয়াত nf দেখিবা কেতিয়াবা ইয়াত nf দেখিবা ইয়াত ni দেখিবা it depends upon are you talking about absorption spectra or emission spectra okay so if you are talking about absorption spectra to initial tumar juntu hobo ei tolat thakibo means n equal to 1 or pora ahe suppose n equal to 1 or means what I'm saying if you are talking about absorption spectra then definitely ni will be less than your ni will be less than nf isn't it so definitely 1 by ni will be less than greater than your 1 by nf so etu positive ahibo yat ami juntu kore etu positive ahibo suppose we are talking about emission spectra ki hoy electron upor pa tolle ahe it jump from upper level to down below tolo level e ahe that means your initial stage will be higher than final stage so emission spectra kan etu ulta koi diba tumi yak efale loi ahiba yak efale loi ahiba nije kori saba gom pabai nohoy karon wavelength value to negative ahibo noare to jodi negative ahi ase that means either you are doing absorption or tumi uliaisa emission kiba ulta hoy ase tar thik ase that part you can do no issue so kali junta ami kotha patisilu je system to energy release kore absorb kore ba emit kore they do like this they follow this principle okay you simply have to write this 1 by ni square minus 1 by nf square calculate koriba multiply koriba he outside constant term logot then you will get the 1 by lambda value in centimeter inverse or khon dia agore sai so ami term value is also in its centimeter inverse so hetu ako ultimately energy represent kore term value bahi jua mane energy bahi jua bujay হয় নহয় because term value আমি just অকন দিয়া আগতে চাই আহিছিলো নহয় lastত এইটো term value is simply is equal to energy by hc hc to কি আর constant that means energy বাহি যোৱা মানে term value বাহি যোৱা আৰু তুমি ইয়াত এটা কি দেখিছা এটো কি centimeter inverse 1 by lambda so যদি 1 by lambda value বাহি যোৱা মানে কি energy value বাহি যোৱা মানে হল because সেইটো term value centimeter inverse আৰু term value energy বাহি গলে বাহি যায় similarly 1 by lambda centimeter inverse okay so that means we are talking about energy here kiman energy radiate koribo beshi koribo ne kom koribo so if 1 by lambda value higher value then beshi energy radiate koribo by absorb koribo if it is absorption spectra e absorb koribo if it is an emission spectra it will emit the energy okay so yaki ami sai kine ami tumar corresponding atomic or emission spectra form koru for example say this is okay so this side we put energy we don't put energy now you can put energy in centimeter inverse or you can put 1 by lambda this is also in centimeter inverse same thing okay so if I say I have a line here that means what say its value is 2 centimeter inverse okay so that means at 2 centimeter inverse corresponding kibara energy ulabo 2 centimeter inverse tumar electron means that enoka level ase electron jot electron eta value pora n equal to suppose 3 4 pora n equal to 5 like jump korile and jump kora karone tumak absorption spectra at 2 dile or jodi emission kotha ko ta ulta to koi di etu emission hoy jabo ঠিক আছে but now suppose you are observing about hydrogen spectra ঠিক আছে তুমি hydrogen spectra চাই আছা তুমি z equal to 1 put কইলা সব কইলা এই আগৰ যোনটো আমি ইকুয়েশন পাইছিলো লাস্ট স্লাইডত এটু পালা তুমি এই সব জানা তুমি এই সব ভ্যালু পুট কই থইছা ওকে হাইড্রোজেন তুমি এটম চাই আছা নাও সাপোজ তোমাৰ এনেকুৱা এটা ভ্যালু আহিলে সে এনে তুমি হদাই কৰি থাকা তোমাৰ 2 আহিব লাগে তুমি এদিন কৰি চালা তোমাৰ কিবা অকমান এলিমেন্টে চেঞ্জ হলে কি হল হাইড্ৰোজেন আছে তাত বাই দ্য ৱে but তোমাৰ borer according to theory 2 আহিব লাগিছিলে but you are getting your line either in 2.1 or in 1.9 এটা ঠিক আছে এটো either তুমি 1.9 centimeter inverse পাইছা বা 2.1 ত পাইছা centimeter inverse পাইছা কি পাইছা absorption spectra সে absorption or emission জি ধৰা according to theory the value should come at 2 but you are getting either 2.1 or 1.9 ঠিক আছে, you are getting the line like on that position, but your theory is saying that you should get line around 2 centimeter inverse, exactly 2 centimeter inverse, for example, but you are getting at 2.1 or 1.9. That means 0.1 or displacement hoise, either plus minus kibara hoise. That means theory by junto value aise, experiment by value to aha nai. I have already said you today yesterday as well, in atomic physics we always follow the experimental results. We are just going after the experimental results and we are just modifying our theoretical concept. So if you are not getting the exact value from theory what the experiment is showing, then that means there is some fault in your theory. Now we will try to rectify that fault. So we'll bring the consideration of reduced mass. Now till now we were thinking that nucleus is very heavy, it cannot move, and only electron is moving. Now we will change our concept, and for a moment we'll try to bring the concept that nucleus is also moving. I mean, the nucleus imano heavy no hoy je jagate roi thakibo, it can also move. Okay, it can also move. I mean, here to concept animatia. We are just trying. I mean, najano etu solve korile je amar enoka jono 2.1 বা 1.9 ahi ase values, for example 2 rahibologia to solve hoy jay niki, but we will try and see whether our energy formula changes or he change to yalagot milibon nai. Okay, because tumi tomak kele koi aso, you see here in your 1 by lambda expression you have r infinity here, and r infinity carries the mass of the electron, and r infinity says the concept that it's a Rydberg constant for infinitely heavy hydrogen, sorry, nucleus. That means the nucleus is not moving in this concept. So jodi nucleus to ma move hoy ase boli dhori lo, আর যদি কেনবাকে মাস তো মই চেঞ্জ কৰি দিব পাৰো, এমৰ জাগাত বেলেগ কিবা ৰাইন দিব পাৰো, দেন হে r infinity value to change হ'ব, and maybe হে r infinity value যদি change হয়, then 1 by lambda value change হ'ব, isn't it? So it might be that can be a solution to our problem. So let us check theoretically. So what concept we'll bring here, we'll try to form a rotor. You have studied that rotor earlier. What I'm doing, I'm just let us consider the nucleus is in this side. This is our nucleus, so I'm just drawing it big, and this nucleus is your attached to the electron, which is very small. Let me, this is electron. Okay, so the distance between them is the radius of the atom. So radius se hobo, so let us draw that. Say yar pratma yar leke. Okay, say it's r, the radius r we are already using in our expressions, and say suppose this side I have the big nucleus this side, and this side I have a small electron. Okay, very small electron this side. Now you know about center of mass system. If one part is very heavy, one part is very light, then your center of mass will move towards the heavier side. And if this side is your if I have a nucleus is this side, okay, then your center of mass will not be at center, look towards your nucleus side. So that means say the center of mass is here. So this is my center of mass, say C. Okay, this is my center of mass. Now let us put the distance. So the distance of electron from the center of mass is x. So this is x. So if this become x, then definitely this will be your r minus x. This will be your r minus x. Okay, so nucleus of center of mass distance to r minus x ho jabo, and electron mass so distance from center of mass is x. Now they are moving. The one side you have the heavy nucleus, and one side you have a tiny electron. And now earlier we were thinking like this only electron is moving around their nucleus. Now here we are considering that both my nucleus and electron is moving like this. Okay, you can just think about a rotor. Now why I'm so worried about the rotation? Because while deriving the Bohr's energy, you use the postulate of Bohr, where he said that angular momentum of the electron in a given orbit should be equal to nh by 2 pi. Now that angular momentum can have the contribution coming from the nucleus as well. If my nucleus is also rotating, it's also revolving like this, okay, along with my electron, then there can be a chances that the contribution from the nucleus is also coming. If I'm writing as angular momentum of the atom, so it cannot be only the angular momentum of the electron. If my nucleus is also moving, then I have to add the value of the angular momentum of your nucleus as well. Earlier we were thinking that the nucleus is at rest because it's too heavy to move. But now we are thinking, considering that maybe nucleus is also moving. If it is moving, then you have to consider its angular momentum as well, because both will get add up. You have to add both of them, vector addition, and you have to produce the total angular momentum. Okay, so now if that is the case, and now we have created a scenario where this electron and the nucleus are attached by like a pan or wire. It's like a rotor, sorry. You have like, it's like a dumbbell, but one side of dumbbell is very heavy, another side is very tiny, and they are attached by a line if they are moving like this. Okay, so now you have heard a term called moment of mass. This kind of term is used when the two different bodies are attached by a single wire, say a rope or a rod, and one is very heavy, one is very small. Then you use this word called moment of mass. Means moment of mass means at equilibrium. Suppose here is the big nucleus and here is a tiny electron. Now I have to balance this rod. তোমাকে প্র্যাকটিক্যালও কৰিছিলা নাইফ এজে তুমি ব্যালেন্স কৰিব লাগে. Okay, I think in bar pendulum you have to balance your scale bar pendulum in your scale, that pendulum to a knife edge to just find out the center of gravity of the bar, that pendulum. Okay, similarly just think about like this. Here you have a big nucleus and you have a tiny electron here, and you need to balance this. What balance koriba? Center of mass of the balance koriba koi kine. Okay, so at equilibrium means suppose you are balancing and the thing is perfectly balanced. So at equilibrium, the moment of mass means, so this its mass is capital M and its mass is small m. That means the capital M into distance from the center of mass, that is r minus x, should be equal to the mass of the tiny electron multiplied with the distance from the center of mass mx. Okay, that should be the case. This is called at equilibrium. You can say at equilibrium, the moment of mass comes like this. The moment of mass should be equal of both the things. So now you have written m x is equals to m r minus x. Okay, let us just solve this. Mr minus mx equals to mx, or I can take this side to this, so I'll get m plus m x, and this side I'll have mr, or I can write x is equals to mr divided by m plus m. Okay, this I get. So this is equation number 1, and this is my equation number 2. So I got the x value, x is equals to mr m plus m. Now once you get the value of x, huh? Now you just put the value of x in equation number 1. So let me write it here. Let me just make a border. So this is my border. Border means I'll write this side. Okay. So now here I am writing. Equation 1 again implies you don't need to worry about writing all these things because I'm recording the session. So am I recording the session? Yeah, I'm recording the session, so you can write it later as well. So equation 1 implies you have m r minus x is equals to, you can write m r divided by m plus m, or you can cancel out this. You'll have r minus x is equals to mr divided by m plus m. So r minus x is equal to mr by m plus m. This is equation number 3. Okay, so you got the value of x and you got the value of r minus x as well. So now in the next slide we'll be writing the total angular momentum of the atom. So total angular momentum of the atom will be the addition of the angular momentum of both electron and nucleus. I'm doing it scalar addition, so I don't have to worry about the direction of angular momentum. I'm just adding it by scalar. Okay, if I'm doing a vector addition, then I have to worry about direction, but both direction will be same. Okay, because both are moving, rotating, revolving around in the same direction. And if this thing is moving like this, okay, suppose I have here the nucleus and this is a tiny electron, and both are rotating like this. So can you tell me what is the angular velocity of both? Will it be let me go to the last slide. Suppose these things are moving and moving with respect to the center of mass, say from here. So if it's moving like this, let me give a direction. So it is moving like this, in this direction, and I would say, okay, like this, together like this. Now say the angular velocity is omega. Now the interesting thing is that the nucleus and the electron are attached by a single rod. Okay, and the both things are moving like this. Now both will have same angular velocity. You have studied that kind of thing while calculating the moment of inertia in earlier classes, in earlier means semesters. Okay, so both electron and nucleus will have same angular velocity omega. They will have a common angular velocity because they are moving and they are connected to a same rod and they are rotating. Okay, so let me go to the last slide. Okay, so the total angular momentum of the atom will be, first I'll write mr square, sorry, not mr square. First I'll write the angular momentum of the electron. So for electron, its distance from center of mass is x, so it will be simply mx square omega. Mx square omega. Okay, and for the nucleus, its distance from center of mass is r minus x, so it will be omega. We don't know how this angular momentum is this, because angular momentum is simply mvr. V is equal to r omega, so you put r omega here, already r is there, so you'll get mr square omega. R is the distance from the axis of rotation. So for electron, the axis of rotation is distance is x, because the center of mass, the position is the axis of rotation. And for nucleus, the distance from the axis of rotation, that is the center of mass, is r minus x. So in place of r, you are writing here r minus x. Everything is same. Okay, this is your angular, total angular momentum. Now you can put the value of x here. So your x value was capital M, small r, I think. Let me check the value. Small x is, yeah, mr by m plus m. So mr by m plus m, it's a square, everything is square, and you have omega here, plus m. Now your r minus x value is, r minus x was small mr by m plus m. So you will have a small mr by m plus m. It's a square, 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 and you have omega here. Okay. Now I think we'll get some common here. Let us take m, and omega as common, and outside we'll get m plus m whole square as common. So what left inside? M. So one, again, r square is also common, I think. Yeah, take r square as the common. So what left inside? You'll have m from here, the first term, and from the second term you'll have a small m. Okay, so that one is gone. So you'll now have m omega r square divided by m plus m. So your angular momentum is coming out like mm divided by m plus m into r square omega. Now I have already shown you this is our angular momentum, isn't it? This kind of expression you generally get in angular momentum. This is the expression you got from Bohr's postulate as well. L is equal to mvr, or in place of mvr you can write mr square omega. Now you see r square is there, that means distance part is covered, omega is also there. Okay, but instead of one mass you have this thing, by m plus m. Now first of all, let's take the dimension of this. What we'll get if I put if I take all in SI, I'll get kg into kg divided by kg, gone, remain kg. That means the dimension of this is the dimension of a mass. Okay, that means it is representing a mass. So I will name this as, say, mu r square omega. This mu is representing that mass given by this term. Okay, now let us check what is this mu. So this mu is coming as m by m plus m. Okay, or I can write m divided by 1 plus m by m. Okay, I can modify that above equation, mu is equal to. Now generally our mass is a small m. No matter you go to energy value or Rydberg R infinity value or the angular momentum postulate of Bohr, everywhere your mass is small m. The small m is the mass of the electron. Now you just check here, your small m is divided by something which is 1 plus. Now this m by m, I know its value will be very small, but no matter, even it is very small, it's still 1 plus. Okay, that means denominator is more than 1. That means what? Your mu will be always less than m. Maybe it can be there can be a very small difference between mu and m, because this small m by capital M will be very small, because mass of electron versus the mass of nucleus is a very small quantity, but still it's 1 plus. So it can be like 1 plus 0.000001. Still it's 1.0001. So 1.0001 is always greater than 1. Okay. So it might not affect any other calculation, but in reality it's smaller. The 1 is always smaller than 1.000001. Now that means your mu is always less than m. The m is the mass of electron, which we are using generally, which we are using in earlier our calculation. But now this mu is less than m, and that's why this mu is known as reduced mass. The original mass is reduced by which factor? By this 1 plus m by m. Now this thing will definitely impact our energy calculation, or you can say our R infinity value. So the Rydberg constant, the R infinity was earlier. What was R infinity? R infinity was R infinity was, yeah, me4 by 8 epsilon naught h square. Now this, in place of m, you will have what? You will have mu. That will be a new Rydberg constant, isn't it? So say we go to that. Say we go to that. So say we are now studying the variation of Rydberg constant with the reduced mass. So earlier the R infinity was m e to the power 4 8 epsilon naught square h square c, and now this R, say mu, is equals to, you have mu e to the power 4, or in place of mu, let me write here capital M. 8 epsilon naught square h square c. So I had my R infinity. Why I use the term infinity there? Because I was representing that this represents the infinite mass of the nucleus. So what is the mass here in nucleus? যেতিয়া মই mu পাই গলো reduced mass, ইয়াত মই consider কৰিছো mass of nucleus as capital M. So since this bottom, this suffix is just representing the consideration of mass of nucleus, so ইয়াত মই infinity দিলো, so ইয়াত মই capital M দিম, because ইয়াত এই second case যত মই reduced mass concept আনিছো, তাত মোৰ nucleus mass capital M ধৰা হৈছিলে, ঠিক আছে, just a consideration, nothing else. So let us modify this. Mu is equals to what? We know m e4 8 epsilon naught h square c. So mu mane ki asle m divided by 1 plus m by m. Eta ami yat likhilu moi. So 1 by 1 plus m by m. So mu value put hoi gol de yat. M to yat likhilu aur baki khini moi ifal likhi dilu. So what is this? This is R infinity. So that means R infinity is equals to 1 plus m by m. And this side I have Rm. Which means what? Your Rm is less than R infinity. Okay. If my Rm is less than my R infinity, will it impact my absorption spectra or emission spectra? Yes, because your 1 by lambda was nothing but initially it was R infinity z square, and you had 1 by ni square, say minus 1 by nf square. Okay, this was your absorption or emission spectra. Yes, so it 1 by lambda to me pi centimeter inverse. So now this R infinity is no longer R infinity, it has become Rm, and Rm value is less than R infinity value. ঠিক আছে, Rm value is less than R infinity value. That means যদি মই ইয়াত Rm লিখি দিম in place of R infinity, 1 by lambda value কি হৈ যাব? কমি আহিব। আগতে যদি ই 2 পাই আছিলো, এটা তাৰ value 1.9 হৈ যাব পাৰে, for same atomic number and same level of transition. ধৰা n is equal to 1, nf is equal to 2 আছিলে, হাইড্ৰোজেন ধৰি লোৱা z equal to 1, যদি মই R infinity ধৰো, maybe 2 আহিব পাৰে, 2 centimeter inverse 1 lambda value, but যদি মই Rm ধৰি দিওঁ, তেতিয়া মোৰ value 1.9 আহি যাব পাৰে, because Rm is less than R infinity. That means what? That means if according to Bohr or using R infinity, the spectra, the absorption line or the emission line should come at 2 centimeter inverse, then using reduced mass effect, it should come 1.9 centimeter inverse. So 2.1 nohoy, etu bad dia etia. So etia 1.9 gusi ahilu ami. So that means 2 jagar 1.9 hobo pare. So if experimentally you are getting 1.9 centimeter inverse, jor ki Bohror mote 2 ahibo lagisile, that means the system is following reduced mass effect. Now you might ask the question, sir, moi can I gom pam system to reduce mass effect so kori ase ne normal kori ase? Then I'll suggest you always use the reduced mass system. Reduced mass to use koriba because that is more accurate. Okay. Our next one to pohim, it is relative Sommerfeld theory. That to me dekhiba, about G to me paba, here board bad dikin to me Sommerfeld use korai bhal. Aru agbahi jaba, you'll get vector atom model, then you'll see the vector atom model concept use korai bhal instead of Bohr or reduced mass or rather or your Sommerfeld. So one by one modify kori goi thakim theory pur. One by one upgrade kori goi thakim. So this reduced mass system is the upgraded version of Bohr's theory, general theory. So definitely tomorrow experimental result aru besi bhalke explain koribo paribo. Aba all of the asile tomar limitation of Bohr regarding the mass of the nucleus or movement of nucleus will be sought out in this case. ठीक है? This is the first modification of Bohr. Okay, I hope you got it. So in the next class we'll move in the next part. So tomorrow ki koriba, you go through the book and in book tumi a reduced mass effect to pohiba yar karone ki changes ahibo pare aru yar experimentally hosake kuntu system paisile jenoka changes. In example you might get the case of deuterium. What is deuterium? Deuterium or tritium, they are the isotopes of hydrogen. Hydrogen we know na, hydrogen is 1H1. This deuterium is if I'm not wrong, it's 1D2, means you can write 1H2, or this tritium is I think if I'm not wrong, it's 1H3. See, what is increasing? Atomic number, that means number of electron is same, everywhere is 1. Okay, so what is increasing? Here it was only one proton, so nucleus had only one proton, but here the nucleus has now one proton and one neutron. That means the mass of the nucleus overall has increased compared to hydrogen. Similarly, in 1s3, we have one proton and two neutron. So the mass of the nucleus has increased compared to simple hydrogen. Okay, so there is a hydrogen or kind 2 paisila, suppose 2 centimeter inverse of paisila, kibada spectra. Then it may be that if your system carries, instead of hydrogen, if you have a deuterium, which is also an isotope of hydrogen, then it can be, it is possible that tomorrow spectra to 1.9 of gusi ahibo pare, because tomorrow nucleus or mass to heavy hoy gol agotke, aru eta tomorrow etia play koribo pare. Keneke play koribo pare? Because now the reduced mass system might come and take action. So you go through the books, because see, I can only guide you. After all, you have to go through the books. Very much of notes for then it will be injustice to you, because তুমি যেতেলা কিতাব নিজে নপঢ়া তোমার idea আর clear নহয়. So you go through any book you follow. Rajkumar follow koribo para, it's a very good book. You can follow this is called White eta book ase, hetu follow koribo para, or you can follow this. I have one book, what is name? It's wait, it's by Kulia, SP Kulia, hetu follow koribo para. Okay, you can follow any book. Thing is, but at least follow one book. Purely eta book follow kora, and jiman para etu reduce mass system or example bur check koriba. Okay, so I think ajir karone hobo. I think we have a offline class tomorrow, so we'll meet tomorrow in our college. Okay, so thank you very much.